Welcome back to this video lecture series on data structure and algorithms. So today our lesson is the introduction to AVL tree and insertion operation to AVL tree. So what is AVL tree? Named after their inventor Adelson, Velsky and Landis, AVL tree is a self-balancing binary search tree where the difference between the left subtree and the right subtree is never more than 1 for all of the nodes of the tree. This difference of height is actually termed as balance factor. So to differentiate, we can take up this example of these two different diagrams. On the left hand side, we can say that this is an AVL tree. Why? Because for any of the nodes, the height difference between the left subtree and the right subtree is never more than 1. So if we take up this example of this node, then we can say that the height difference between this left subtree and the right subtree is 1. Again, let's take this node. So this is the left subtree, this is the right subtree, and the height difference is 1, not more than 1 for sure. And coming to this right hand side, we can see that this clearly is not an AVL tree. For example, if we take up this node 12, we can see that the height of its left subtree is 1, 2, 3, and for the right subtree is 1. So 3 minus 1, 2. So the height difference or the balance factor is more than 1 for this node. We can also check that for this node also, the height difference between the left subtree and right subtree is more than 1. So it definitely is not a self-balancing binary search tree or an AVL tree. So this is very important and significant question, that why we should be bothering about this AVL tree. The thing is, the time consumption for most of the operations that we operate on a binary search tree, that depends on the height of the tree. Now if the binary search tree is a skewed binary search tree, then the cost becomes big O of n. That is, it depends directly on the number of nodes or the number of levels. And skewed tree means where every node lies in the same direction, like leftwards or rightwards. So here, what is the advantage for using AVL tree is that AVL tree always persists its feature of self-balancing. Thus, using AVL trees for all of the above operations that we generally operate on binary search tree would take a time consumption equivalent to big O of log n. So the time consumption, the time complexity reduces significantly. So now let's move on to the insertion in the AVL tree, how to operate that. So there are very basic 5 steps to do the insertion operation. At the very beginning, we do the normal binary search tree operation. That is the way we do the insert operation for binary search tree. The current node must be ancestor to the newly inserted node. Now after doing the insertion, we update the height of the current node. Then we get the balance factor of the current node. Now if the balance factor is greater than 1, then it is left case or left right case. And if the balance factor is lesser than -1, then it is right case or right left case. So here we encounter with these terms left case, left right case, right case, and right left case. So let's have a look at the meaning of these terms. So what is left and left right case? In this diagram here, or in this left hand side, we can see that this is not an AVL tree, obviously because the height difference or the balance factor is more than 1. So now this situation is called left case because you can see for this root node, the first child is on the left side and also the next child, due to which the height difference between the two subtrees of this node becomes more than 1, also lies at the left side. So it is called left case. And at the right hand side here, although the fact that the height difference between these two subtrees of this node remains more than one, that is, it still is not an AVL tree, but the difference between this and this is that the next child to this, due to which the height difference does not remain 1 and it becomes more than 1, lies at the right hand side of this node. So this is called left right case. And using the same logic, the right case and the right left case, these are self-explanatory. Now question comes, whenever we encounter these kind of cases, how to deal with that? For that we have two strategies. One is called the right rotation, another is called the left rotation. So let's have a look at those. So this is the right rotation. This is nothing but whenever we encounter a tree which is in left case and is not an AVL tree, to make the tree balanced and to make it an AVL tree, we operate right rotate or right rotation on this tree. So for this example, in this left case, we always apply the right rotation. Here we can see that for this node, the height difference between the two subtrees is more than 1. So we right rotate this node. What we do, we simply store this node and this node into temporary nodes, and then make this node as the root node, and we make a connection between this node and this node, and finally we get this balanced tree here. See, one thing, whenever we do this right rotation, all the properties of the nodes, that this node has higher value than this node has higher value than this node has lesser value than this, everything is kept same, nothing is distorted. What we do different is that we make it a balanced tree. That is, for any of the node, the height difference between two subtrees is never more than 1. And for the left rotation, well, this process is same, just like right rotation. The difference is that whenever we encounter right case, only then we apply this left rotation. So let's now jump onto the programming part and let's see how we can implement this insertion operation on AVL tree. Okay, so I have opened my IDE and this is where I'm going to code it. So we'll be starting with first defining the structure of the nodes of the AVL tree. So we have already seen the structure of the nodes of all the binary search trees or binary trees. The only difference here, that apart from the data value and the pointer values, we'll be having another field which is called as height, because that's what we are going to deal with whenever we are talking about AVL tree, that is balancing the tree in terms of height. So let's first just define the node. So struct node, the first field will be data, next will be two pointer fields, so struct node star left and another will be right. So, and the last field will be, which is new here, height. Very well. So here I'll first take a variable of this type and name it root and give it a value of null. Okay, so now I'll be calling the insert function. So this is the actual function through which we'll be operating the insertion operation. So the arguments to this function will be the root node and a value. So I'll be calling the function several times, so let me just copy this line of code and paste it for several times again. Let's say 20, then 30, then let's say 40, 50, and lastly let's say 25. Okay, so this is the thing. So let's move forward and define this function. So copy it, and paste. So the return type will be struct node star. I'll copy this because the argument type will also be the same. So struct node star a root node, and this will be, let's say, val. So what we had seen that the algorithm said, we first have to execute the normal BST insertion. So let's move forward. If R is null, then we'll simply return a node which will contain this value. So a node, for that we'll use another function, new node, and the argument to this node will be val. So I'll be defining this function also, new val, new node actually. So struct node star, this is the argument. Here we'll first struct node star temp, allocate the memory for it. So struct node star using the malloc allocation, size of struct node. Now allocating the value, so temp data will be having the value of val, temp left will be having a value of null, then temp right will have a value of null, and lastly, for all the cases, the height of each of the node will be assigned with a value of 1. Lastly, we just need to return this temp. So this is now another case is that if the value is less than the data value of the root, for that case what we'll be doing is r left is equal to a recursive call to this function, and the arguments will be changed as r left comma the val. Right, now else if another condition, if the val is greater than the r data, then we'll say r right is equal to again an recursive call to this function on the node r right and the val. Lastly, else return the root. So after doing this normal BST insertion, we need to update the height. For that, our height will be 1 plus, here we will use actually two functions. So first function will be a max. This function will determine the maximum of two values. Now these two values will be, one is height of the left subtree and another is height of the right subtree. For determining the height, we will also again use a function and we'll name it as height. So height of the left subtree and height of the right subtree. So now we'll first define this max function here. This will return an integer, so int max. This will take two values as arguments. Let's name them a and b. We can simply use this condition that if a is greater than b, then return a, else b. We'll just space it out a bit so that it looks okay, and let's keep it in a parentheses. So this yeah, I'll keep this whole in a parentheses. So this is the max function, and another function which is height. This will again also return integer type. So int height, argument will be struct node star, let's say r. Now the first condition checking will be if r is null, then we'll say return 0, otherwise we'll say return r height. So this is the height function. So after updating the height, this is the time when we'll be having a look at the balance factor and then determine what are the cases, left or right or any other, and then we will operate the rotation functions. So before all of that, we first have to determine the balance factor. For this, let us just take this variable, say balance, and use a function. Let's name it get balance. The argument will be r to get the balance factor. So we'll first define this get balance function. So here I can define it. The argument will be struct node star r. The return type will also be same, so I'll be copying it. So okay, so the return type will be actually int, sorry, here. So if we see that the root or the node passed to this function is null, then we'll simply return 0, otherwise we will return the balance factor. So balance factor is nothing but the height difference between the left subtree and the right subtree. So we'll type return height of the left subtree minus height of the right subtree. I'll keep it in parentheses, yeah. So that's it. So now we'll have to check for the conditions. The first condition is left. So if the balance is greater than 1 and the value is less than r left data, then it is a left case. For that, what we'll be doing is a return will actually operate the right rotation on the root node. This is the left case. The next case is left right. For this, the condition will be if balance is greater than 1 and the value is greater than r left data, then what we do first is r left is equal to left rotate r left, and lastly we return right rotate on the root. So for this line, that why we operate the left rotate and then right rotate, let's go back to the slides and have a look at it. So here we are back to the slides. So this is the left right case as we said. So now why we did operate first a left rotation then a right rotation? The thing is that here if we consider this node, then this is at the left and this is at the right. So for this node, we actually have to operate a whole the left right case rotation. So we will be dividing it. For this node, the case is right right. You can see these two consecutive child nodes are all at the right side. So for this particular node, we can actually operate the left rotation on this node. Now what we'll do, it will balance this left subtree of this node, and then we will get a left left case. So after doing this, we can finally operate the right rotation for this node, because then it will be a left left case. So that is the logic behind doing first the left rotation and then the right rotation. So coming back again, this was the logic for left right. The same logic will be applied when we will be encountering the right left. So before that, let me type the condition for the right right case. That is, if balance is less than -1 and the value is greater than our right data, then we will be saying that return left rotate R, and lastly right left condition, that is, if balance is less than -1 and the value is less than our right data, then our right will be right rotate on this our right node and return left rotate R. So okay, this is not rotation, let's name it rotate only. And lastly, the last line will be here, return R. So we have to define this left rotate and right rotate functions. So let's do it first. So the return type will be struct node star again. First, let us define this left rotate. The argument is a node again, so struct node star R. So we first will take some node variables and will store some values. So here in this left rotate case, we'll first store the right node, then we'll again take another node, let's name it Y, and we'll store the left of it. Now we'll do these link changes in the tree, that is, A left will be R and R right will be Y. Lastly, we'll have to update the heights of both these A and R nodes. For that, again, I'll be using max function, height of A left and height of A right. Now updating the height of the R, one plus max height of A left height of A right. Lastly, we'll return this A node. This is the code for, this is the logic for left rotate. The logic for right rotate is almost same, so I will be just copying this lines of codes. The changes here will be, first the name will be right rotate, this will be left, our left will be stored here, the right child of this will be stored here. Now here this will be our right, this will be left. The height updation, these will remain same, and the return is also same. So insert function is complete here. To check whether we did right or wrong, we'll simply do a pre-order traversal. So pre-order traversal of the AVL tree is a new line. We'll just define a function, pre-order, so yeah, we are only left with defining this pre-order function. So let me just copy it. So the return type will be void, and this is the function name. The argument is struct node star r. So if r is equal to null, then write return simply. Otherwise, for the pre-order traversal, we first print, that is %d space, this will be r, data, then we will do a recursion call on the left child, and lastly another recursion call on the right child. So this is the code. Let's now run it and see how the program works. So here is the output, and as we did insert these values, we can see a perfect pre-order traversal of this. So this was the introduction to the AVL tree and how you could implement the insertion function. Thank you for watching this video and staying with us. See you next time.